In this lesson, we're going to cover some infrastructure considerations. Now, our network infrastructure forms the backbone of all of our information technology environments, and requires us to make a wide variety of decisions when we're designing the architecture that can potentially impact the efficiency, security, and resilience of our networks for years to come. These infrastructure considerations and decisions include things like the correct placement of your devices in the architecture, the use of security zones and screen subnets, understanding your attack surface, determining your connectivity methods, understanding your device attributes, and configuring the failure mode to utilize when things go wrong. Now, first, let's consider the placement of your devices inside of your network architecture. The location of your devices, including things like your routers, your switches, and your access points, can greatly influence both the performance and security of your entire network. The proper placement will ensure optimal data flow, minimizes latency, and it provides a robust defense against potential security breaches. For example, by placing a router at the network's edge, you can help direct and filter incoming and outgoing traffic much more efficiently. Access points should also be strategically positioned to provide adequate coverage while attempting to keep all of your wireless signals located inside your facilities and to ensure interference between your system and others is being avoided. Switches, on the other hand, are going to be designed to serve as the main connection point for most of your network devices, and so they need to be placed in a position that allows for your various devices to be easily connected to the proper physical segment of that network. If you place your devices in the wrong places, this can lead to network bottlenecks, vulnerability points, or even areas without connectivity. So it's really important that you carefully plan and evaluate your placement decisions while designing your network's architecture. Second, we need to consider how we're going to configure security zones and screen subnets in our network architecture. Now, a security zone is a distinct segment within a network, often created by logically isolating the segment using a firewall or other security device. These security zones or segments are going to be designed to contain devices with similar security requirements and levels of trust. For example, a company might have different zones for its public-facing services, internal employee resources, and sensitive data storage, and each of these will be configured with different access controls and different security policies based on the sensitivity or classification of the data contained in each of those security zones. Now, a screen subnet can also be created to act as a protective layer or buffer zone between an organization's internal network and an untrusted external network like the internet. A screen subnet used to be referenced as something known as a DMZ or demilitarized zone, but in recent years, this term has been changed to a screen subnet instead. Note though, some network appliances and equipment that you might use on a daily basis may still use the term DMZ or demilitarized zone when you're configuring them, but for the exam, you should remember the term screen subnet instead because that's the term you're going to be asked about. Now, a screen subnet is used to host public-facing services like web servers, email servers, and DNS servers, while ensuring that if a security breach occurs inside of that screen subnet, the attacker will not have direct access to the core internal network that contains your most sensitive data or systems. This screen subnet is going to be used to provide an additional layer of security to make it harder for a malicious actor to reach the innermost and most valuable portions of your organization's network. Third, we need to consider the attack surface that our network architecture is going to represent to our organization. Now, the attack surface of a network refers to all the points where an unauthorized user can try and enter data to or extract data from an environment. In essence, it's the sum of all the potential vulnerabilities and risk points inside of a system, a network, or an application. As our networks grow and become more complex, and we add additional devices, applications, and access points, the surface area and the attack surface will inevitably expand and become larger and larger. A larger attack surface generally equates to a higher level of risk because there are more opportunities for malicious actors to exploit weaknesses and vulnerabilities in your systems, including improper device placement, improperly configured devices, outdated software, unnecessary open ports, and weak access controls that are being used. To reduce your attack surface, you need to identify the vulnerabilities and either eliminate them or implement proper controls to mitigate the risks associated with those vulnerabilities. To safeguard our organization, it's really important that you regularly assess and minimize your organization's attack surface. By taking a proactive approach, you can ensure that you remain conscious of any potential threats and that you can act swiftly to address them in order to maintain the integrity and security of your organization's network. Now, fourth, we need to consider the different connectivity methods that are going to be used for our network architecture. Connectivity refers to how different components of a network are going to communicate with each other and with our external networks. The connectivity method that you choose will really influence the performance, reliability, and security of your entire network or system. So, if you're going to use a traditional wired network connection, like Ethernet, this is going to provide you with higher levels of stability and much faster speeds, but it is going to be more restrictive in terms of your end user's mobility than using a wireless network, and so it becomes much more difficult to move workstations and laptops to different offices because the wired cables will also have to be moved or new ones will have to be installed to support your new office location. On the other hand, wireless connectivity methods like Wi-Fi, microwave links, and satellite connections do offer us greater levels of flexibility and scalability because they're not limited to the pre-existing wiring of a given network. But they do suffer from interference and potential security vulnerabilities if you don't properly configure your wireless devices. Furthermore, newer wired methods like fiber optics do provide higher speed data transmission over longer distances with minimal signal degradation than a microwave link or a satellite connection would. Sometimes, to create a more robust connection, you might use a hybrid method that's going to combine various forms of connectivity to leverage the strengths of each different technology that's being used in order to ensure additional layers of redundancy are being put into your networks. Now, when you're designing or revising your network architecture, it's essential for you to weigh the benefits and drawbacks of each connectivity method based upon the specific needs and objectives of your organization's network. You should think about the various factors, including scalability, speed requirements, security considerations, and budgetary constraints when you're determining the most suitable connectivity option for your organization to utilize. Fifth, we need to consider the device attributes that will affect how each device can be utilized in our network's architecture. When I refer to a device's attributes, I'm really referring to whether or not the device is considered to be active or passive, and if it's going to be placed inline or as a tap or monitor inside of your network architecture. Now, active devices like intrusion prevention systems are going to be used to monitor and act on suspicious or malicious network traffic by influencing data flows and making real-time decisions based on the network's current state. On the other hand, passive devices like an intrusion detection system will simply observe and report on the network traffic without actively intervening or altering its data flow. Network security devices can be installed as either an inline device or a tap-based configuration. Now, an inline device is going to be positioned directly in the path of the network traffic, and they have the capability to influence or block traffic as it passes through the device. This makes an inline device, like a firewall, a router, or an intrusion prevention system, a really critical tool for tasks like filtering malicious traffic or optimizing our data flows. Taps and monitors, on the other hand, operate much more discreetly because they're placed outside of the direct network path, and they're configured to only listen to the network's activity by capturing data for analysis without impacting the actual traffic. This makes them ideal for monitoring network health, performance, and security without risking any kind of disruptions to your network. So, when you're selecting a security device to place in your network, you need to ensure that you consider whether it's going to be set up as an inline or tap device to best optimize your network security and performance. Always make sure to align your choices with the network's broader goals and challenges too. For example, an organization that requires real-time threat mitigation might prioritize installing an inline security appliance, while a different organization who's focused more on monitoring might select a passive tap or monitor to use instead. Sixth, we need to consider the failure mode that we want to configure our devices to use in case something goes wrong. Now, the failure mode selected will determine how a device behaves when it encounters an error or malfunction. There are two primary failure modes that we can utilize, and these are known as fail open or fail closed. Now, when a device is set to fail open, it's going to allow traffic to pass through without any inspection or filtering in the event of a failure to ensure that there is no disruption to the network service. If you're operating a firewall that's configured as a fail-open device, that firewall would simply allow all incoming and outgoing data to flow freely through it to maintain uninterrupted network connectivity if something goes wrong. But this firewall is no longer providing you with any kind of security when it's operating in this failed open condition, so it's important to realize that too. Now, if you're using a device that's set to fail closed, it's going to do the opposite, and it's going to block all traffic in the event of a failure to ensure that your security of your network remains intact. If you're operating a firewall that's configured as a fail-closed device, if a malfunction occurs in your firewall, that firewall is going to start blocking all incoming and all outgoing data in order to maintain the security of your data and your network. But this will fully interrupt your network connectivity and prevent any normal firewall operations to occur during this failed state. Now, your choice between using a failed open or failed closed mode is really going to depend on the organization's security policy and the criticality of the network segment that that device is trying to protect. For example, a data center that's used to store all the organization's sensitive financial data might opt to use a failed closed mode to maintain the security of the data in the case of a device failure. On the other hand, if you're operating a guest wireless network, you might prefer to use a failed open mode to ensure uninterrupted access for all of your users because you're not really trying to protect any sensitive data or servers inside of that guest wireless network anyway. So remember, infrastructure considerations play a pivotal role in the efficiency and security of a network environment. Therefore, it's important to consider the device placement in your network architecture so you can optimize your data flow and security. Security zones and screen subnets can also be used to help isolate and protect network segments inside of your architecture. As a cybersecurity professional, it is our job to understand our organization's attack surface and provide ways to minimize it so that our security is going to be increased. Additionally, you need to consider the various connectivity methods that you can use in your networks so that you can choose the right one to provide both the performance and flexibility that your organization needs. As you install various network and security appliances in your architecture, you also need to consider whether they should be placed in an active or passive role, and if they're going to be installed as either inline or as a tap or monitor position. Finally, you should be aware that the failure mode of your various devices includes things like fail open and fail closed, and you need to know what they're going to do and what protections they will or will not provide to you if the device becomes overloaded or fails to operate as designed. By considering all these infrastructure considerations, you can build a more secure network architecture and that the security of your organizational network remains intact.